Good afternoon, everybody. Welcome to another, I guess it's cloudy, not really rainy, a Monday afternoon with your host, me, Dr. White. Me, Dr. White. Do you know what time it is? It's new chapter in functional, or not functional, new chapter time. And I better warn you, this new chapter is very dangerous. It's fattening. Uh, it's real dangerous. It'll get you cavities if you're not careful and put on weight. And what are we going to talk about? Carbohydrates. You know, the three major food groups. We've done fats and oils. We'll do carbohydrates, and later on we'll do proteins, even though you know there are four major: alcohol, beer, or pizza, potato chips, and I forgot the fourth one, salami sticks in my book. But anyways, all right. First, a disclaimer from Dr. White, and that is this chapter, we're going to be talking about carbohydrates, which, if you're reading the book, is chapter 18 and part of chapter 5, which I had skipped. And we're going to talk about in this slide, you do not have to write down anything from it. We're going to talk about things in biochemistry. And biochemistry really is the study of chemical substances found in living things and their chemical interactions with other things. Now, for some reasons, people think you're doing biochemistry and all of a sudden, pookie, we're doing magic. No, you're still doing organic chemistry. It's just in your body or a plant or something that's alive. And the functional group chemistry that you've learned for organic molecules occurs just the same way in bioorganic molecules. In other words, functional group chemistry going on in your body is the same as what we studied, which makes it exciting. And I won't ask you, but a biochemical substance is really a chemical substance like a ketone aldehyde or whatever found in something that's alive, but it doesn't make it any different than if it's outside. All right, switches on. Let's talk about carbohydrates. You should know, what is a carbohydrate? The carbohydrate is a polyhydroxyl aldehyde, polyhydroxyl ketone, or compounds that yield such polyhydroxyl aldehydes or polyhydroxyl ketones upon hydrolysis. That means reaction with water. Now, what's the word poly mean? Many. Hydroxyl OH. That means you've got a molecule that has an aldehyde and a many hydroxyl groups. Polyhydroxyl ketone is a ketone that also has lots of OH groups. Now, I will never ask you to learn the structure of fructose or glucose. Now, this is called the Fischer projection, and I'll teach you later on what that means. But each intersection of a line, here, and here, is a carbon atom. So here we also have a carbon atom, and same thing here, here, here. And notice I have my software for glucose writes an aldehyde, not like this, but like this, which if you go back and look at my slides, I said some people write aldehydes. So this has an aldehyde. And this right here R group carbonyl, R prime. This is a ketone. And therefore glucose, which I'll teach you about, is a polyhydroxyaldehyde. And fructose, which I'll teach you about, is a polyhydroxyl ketone. These are both carbohydrates. Now, normally in our society, when you're talking about your diet, which I got to watch my carbs, you're talking about longer things we call starches. And I'll teach them those are carbohydrates too. But the true chemical definition of a carbohydrate includes more than just starches. Now, if you're a carbohydrate chemist, which I'm not, even though I do consume carbohydrates, well, I like them too much. But anyways, switches off for the following definitions. You have a monosaccharide. And those are carbohydrates that contain a single polyhydroxyaldehyde or ketone. So if we come back here, glucose and fructose are monosaccharides. This I'll never ask you on a test, but your other classes, especially if you're doing anything with food or dietitians or whatever, we'll talk about these. So I want to cover these definitions. So a monosaccharide is a carbohydrate that contains a single polyhydroxyaldehyde or ketone. Oh no. Time flies when you're having fun with soap and steroids. It's time for a break. I'll see you in 5. Come back. Oh, I actually went a little longer than I should have. Come back at 2:55. I'll still let you out on time today. I'll be right back. Sorry about the late start. I'll go an extra 5 out. No. Time to start. All right, thumbs up, people. You see carbohydrate classification on your screen? Now, do you see it on your screen? Thank you. Don't scare me like that. All right. Now, we're talking about monosaccharides, and those are carbohydrates that contain a single polyhydroxyaldehyde and ketone. Remember, switch is off right now. Now, you can link together like a polymer, and I'll teach you that later this chapter, monosaccharides like fructose and glucose and other ones. You can link these together or these together each other or these, not that much these. And you can make what's called, and I don't even know if I pronounced this right, oligosaccharide. Those are carbohydrates that contain from 2 to 10 monosaccharide units. Again, switch is off right now. Now, why do carbohydrate chemists have to have all these fancy names? Don't know. I'm not a carbohydrate chemist, but they do. So I'm introducing you to them. Now, there's one oligosaccharide I do want you to know, and that is a disaccharide. You know, dimethyl, 2 methyl groups. Disaccharides are carbohydrates that contain 2 monosaccharides that are covalently bonded to each other. Now, I won't ask you what is a disaccharide, but the most important disaccharide you should know is sucrose. And you should know sucrose is table sugar. If I ask you what's the common name for table sugar, it's sucrose. And you should know that. Hint, double hint, big hint. I'll never ask you what is a disaccharide, but I'll expect you to know that table sugar has a name, sucrose, and it is a disaccharide. And I'll teach you later on, sucrose is really a glucose and fructose molecule bonded together. Isn't this getting exciting? We're getting into the sweet stuff of organic chemistry. Oh my goodness, I just did a good joke. For those who are into cooking, we're getting deep into stuff in cooking. Now, you can also have what's known as polysaccharides. Again, switches off. And polysaccharides, poly means many. You learned that in polymers. And many saccharides. These are carbohydrates made up of more than 10 monosaccharide units bonded together. And the most common polysaccharides you're familiar with are starches. Starches are polysaccharides. And Dr. White loves his starches. Oh my goodness, look out. There's nothing better than the rotini with some butter and garlic butter on it and a little good cheese on there too. I'll let you pick your favorite cheese. Romano would be my choice. I'm getting hungry already. See how dangerous it is being in my class? All right. Time to slam on the brakes, and we're going to switch to another chapter, and that's chapter 5. Now, some people teach this before we get into carbohydrates, but since you're not going to use it until carbohydrates, I don't do it earlier, I do it now. And I'm going to teach you in this part of the chapter 5, the chemical difference between your right and left hands. Yes, I will. You really? Yep. And this is important. This is an important part of organic chemistry and plays a real important role in carbohydrates. All right, switches on. This chapter deals with chirality. And when we talk about chirality, you should know chiral is the Greek word for handedness. And about 3 summers ago, I actually had 2 students in my class at the same time that were both fluent in the Greek language. And they said, yes, chiral means handedness. And what do we mean by handedness? Carbohydrates exist in 2 forms, like your right and left hand. If you notice there, I have my right and left hand. They look similar, but they're different. And I'll be teaching you how they're different this chapter. But you didn't think I'd get into your hands, and we'll also talk about your feet too. Now, when we talk about chirality, remember, you should know chirality, chiral, Greek for handedness, like your right and left hand. I have to teach you some things. I'm going to assume everybody in our class has looked in a mirror or has access to a mirror somewhere. If we were still face to face, I could say you could go into, at least the men's restroom have mirrors at ECC. I'm going to assume the women's do too. I've never been there, never will. But for those of you who have been in the women's restroom, I assume they have mirrors in there. And in your homes, I'm sure everybody has a mirror in there. Now, there's 2 types of mirror images. One is called superimposable, and the other is non-superimposable. I'll never ask you what is the definition of a superimposable or non-superimposable image, but you should know what it means, because you'll see in a while, you'll have to know the operational definition. Superimposable, that's an image that coincides with all points when images are laid upon each other. In other words, if I have, trying to look for something real quick. All right, hold on. I have a very important warning to tell you. This part, Dr. White's going to do some artwork, and make sure you don't fall off your chair laughing your brains out and hurt yourself. Hold on when you're laughing that hard. I'll never be an artist. My mother was good. Let's look at what we mean. First of all, I think you've all taken and looked in a mirror. You have your image and you have the reflection, your mirror image. Now, hold on. Here it goes. What is this? A sewing needle. The pointy end part, you put the thread in. Yes, you can laugh now. And if I were to hold a sewing needle up to a mirror, guess what I'd see? The reflection. If I were to pick this up and lay it over there, every point or every part of it was superimposed on the other. Here I have a red rubber ball. Plain rubber ball. Those of you know the song, bouncing back like a rubber ball. Never mind. But anyways, if I pick the image up, I can superimpose it on there. Yeah, ooh, I got something I can do. Look out. Great moments in teaching organic chemistry. This is a model. In the center is a carbon atom, and coming out are my 4 bonds. Remember, carbon has, oops, fingers broken again, 4 bonds to carbon. And if this were methane, I have hydrogens here. Oh, I've got another one. And if I hold it like this, here's my methane, here's my mirror image. and notice they're superimposable on each other. The silver goes silver, black, 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 black. This, or my models are mirror images. If I had a mirror right between here, like if you looked here, you'd see this. Hold on. It's easier in a classroom. You'd see this mirror image if my hand got out of the way. And so these are mirror images. If I had a mirror in between them, and they're superimposable. That's one type of mirror image. And there are two types. The other is non-superimposable. That means they're mirror images where not all points coincide when the images are laid upon each other. Now I'm going to teach you something real neat and you can impress your friends, neighbors, and loved ones with. I have a homework assignment for you. What? Yeah, I do. I'm going to assume all of you have access to a mirror. Stand in front of the mirror, or you can sit if you have that kind of mirror. Hold your right hand up there. And what are you going to see in the reflection? Your left hand. And your hands are mirror images. But are they superimposable? Let's find out. Oh, no, they're not. If I line up my thumbs, the rest of the fingers don't line up. Line up my center finger, my pinky and thumbs and everything else don't. If I do my index finger, nothing else lines up. Your hands are mirror images, but they're non-superimposable. So your hands are non-superimposable mirror image. Oh, by the way, I can't resist. Everybody know what this is? Spider doing push-ups on a mirror. Now, true story, I got to tell you about this. This is really funny. I think it was my first or second year teaching this, and students were having a hard time mastering this. So one of them pointed out, you know, you spelled superimposable wrong and non-superimposable. I had superimpossible and non-superimpossible, which is why they were having a hard time, because it was superimpossible. True story. Once I changed it to superimposable, things were better. That's really a true story. I don't know any fake stories. All right, now, when it comes to chirality, hint, switches on big time. Speaking about, first of all, there are two types of objects. One is a chiral object and the other is an achiral. I'll never ask on a test, define chiral or achiral object, but you should know how to identify objects as chiral or achiral. Now, chiral object, that means it has handedness, is an object that is not identical to its mirror image. A chiral object has a non-superimposable mirror image. Achiral, A is the prefix meaning without. Achiral doesn't have handedness, is an object that has a superimposable mirror image. It's identical to its mirror image. So chiral object, non-superimposable mirror image, excuse me, achiral, superimposable. Remember, A means without, which reminds me of a story. Oh, I got time. Yes, I do. When I was a postdoctoral fellow at the University of Illinois Chicago Circle, I was working for, he was a great chemist, organic chemist, and you become a postdoctoral fellow after you've gotten your PhD and you got to move on, but you don't have a real big job. So you work for another professor till you get a real job. and you're pleasantly poor. You get a nice salary, not that great, and you get to learn things. And this instructor, professor, taught me a lot of organic chemistry, and his name was Professor Moriarty, yes, just like in Sherlock Holmes. But anyways, Professor Moriarty, and I don't know if he's still alive or not, but anyways, he's the only person I've ever met in my life that was amoral, not immoral, amoral. He just had no moral compass whatsoever, which means he could be very dangerous. And there are other Dr. Moriarty stories, but I'm not going to tell them. But he taught me a lot of good organic chemistry. And one of the things he taught me was, unlike most academic chemists who spend years on a problem, Moriarty was like a hawk. He'd swoop down on something, and if he couldn't come up with something in 6 months to years, that I'm leaving this, I'm not going to waste the next year or two and find out it still won't work. And that was a very important lesson I learned about research that helped me in industry, which is you either get it done quickly or you move on. So we have two types of objects, chiral object, achiral object. And now let's have some fun. And let's do a couple. And let's look at A. Is A round snowball, perfectly round, a chiral or achiral object? And how do you do that? Well, you've got to consider the mirror image. Oh, by the way, I could use this one. You have a snowball. Here's this mirror image, and it will be totally superimposable. And therefore, it would be achiral because it has a superimposable mirror image. Now, unfortunately, and I'm not going to stand up and stick my feet in front of my webcam, but in a classroom setting, I could direct you down. Is your left foot chiral or achiral? Well, how do you do that? Well, try this in the comfort of your home. Take off your socks or whatever. You have your left foot and your right foot, they're mirror images, but they're non-superimposable. Because let's assume my hands were my feet, even though they're not. Got your big toes, they'll line up and the rest don't. Your little toes, this little one toe, whatever, anyways, won't line up with the rest of the toes. And your toes, your feet are non-superimposable mirror images. And that makes them chiral. So your foot is chiral. Now, anytime, this is a big secret, but anytime you see left or right in a description, that immediately tells you, like your hands, it's chiral. So if I were to say, is my right winter glove chiral or achiral? And immediately you know it's chiral. Now, Let's think about something. Then this won't be on test. How many of you have ever played the game Simon Says when you're young? You know, Simon says this, Simon, I think you all have. Well, let's play Dr. White says. Dr. White says, touch your right cheek. Go ahead. Dr. White says, take your hand off your right cheek. Now, is your face chiral or achiral? Ooh, think about it. You know the difference between your right and left cheek. If I said touch your left cheek, it wouldn't have been the one you just touched. That means your face is chiral, but you never thought about that. You can impress your friends, neighbors, and loved ones next time. Now, let's do a couple more, and I'm going to let you have some fun. Have some fun. Which of the following are chiral or achiral? Chiral, non-superimposable mirror image. Achiral, superimposable mirror image. And just in case you can't read my handwriting, C is a tube sock with no toes. You know how they have, women's have the socks with the toes in them. These don't, or any writing on them. Your pants, the kind with a zipper and button in front. A mitten with no leather palm, and a four-door car. Have fun. Which of these are chiral? Which of these are achiral? And when you're done, give me a thumbs up. And do it again for those people who are on the screen now. If you're done, give me a thumbs up. All right, it looks like everybody's done. Let's go through this. Now, remember, don't fall off your chair laughing. All right, let's do a tube sock. And I would do this on the board, and here, I have a tube sock. no toes. Here's its mirror image. The other tube sock or its mirror image. And guess what? This is superimposable. If I rotate it, it will superimpose. And the other way of thinking about it is, if you have tube socks, does it only fit on your right or left foot? No, you can wear them on both. Therefore, your tube sock has a superimposable mirror image, and therefore, this is achiral, without chirality, handedness. Now, this is a tough one. Now, your pants with a zipper in front and maybe pockets in the back. No, I'm not going to do a drawing of that. But think about it. If you have a pair of pants with a zipper on front, and if I were to ask you, touch your left pant leg, you could. Touch your right pant leg, you could. Now, think about this, and this is something I usually tell in class. If you put your pants on backwards, put your right leg in your left pant leg, and put your left leg in your right pant leg, the zipper will be in behind, and it won't feel right. And I always tell my class, if I ever come into class, my pants are on backwards, someone call for help for me, I'll need it desperately. And if you do the mirror image, it's not superimposable. So those type of things, pants, are, guess what? Chiral. So this one would be chiral. Now, let's do this. Achiral, chiral. And now let's do the mitten with no leather palm. Be careful, this is going to get really funny. See, I'm never going to go to art school. If I have a mitten with no leather palm, and here's this mirror image, and if I rotate this, they'll be superimposable. And therefore, superimposable mirror image without chirality, achiral. And think about it, if you have mittens, or for those of us who have oven gloves, you can put them on either hand when it doesn't have a leather pop. Now, for the piece de resistance, hold on to your chair, people. A car, is it chiral or achiral? Hold on. Here I have a car, there are the wheels. Headlights, steering wheel, brake lights, tailpipe, my 4 doors. And if I did its mirror image, whatever closest to the mirror, I'll see first. My wheels, my doors. Here's the steering wheel on this side. In the mirror image, it will be here, my headlights. And here's my mirror image. And if I pick this up, it's not superimposable. But wait, you say, Dr. White, I can flip this over. Well, if I flip it over so the steering wheels line up, on this one, the tires are pointing down. On this one, the tires are pointing up. And therefore, A car or a truck or a school bus has a non-superimposable mirror image, and therefore it's chiral.
I can tell you're an organic chemist. Your car has an octet rule.
Well, that's general chemistry. What, 2, 4, 6, 8? Actually, with the tailpipe, they're 9 circles. So I just put your observation out of the water. But you're right. Now, do I have time? Oh, I do. Now, I worked for 2 Anglo-Dutch companies, which means I made it to England enough times. Now, one thing, the first time I got to England, luckily I never had to drive for myself. Oh, that would have been a headache. Usually I was with a colleague who had a car, or I had a cab I would take, or I took the train a lot. That was fun, because I stayed a lot of times, usually in Manchester or in Littleborough. I also stayed, but mainly Manchester. I was also in London. But first of all, if you look at the car, notice the one I wrote to begin with. Let's call this Roman numeral 1, and its mirror image, Roman numeral 2. Here, the steering wheel is on the opposite side. And the first time this guy picked me up, who was another manager, we're going somewhere. We come to a stop sign, and he stops, and I'm on the drive. Normally would be our driver's side. I put my foot down to use the brake, even though I wasn't driving. He looked at me and started laughing, an American. Now, the other thing that was quite dangerous, seriously, is if you're crossing a street in England, where in America, the cars, when you're coming off the curb, is coming this way. No, in England, it's coming the other way. Twice, I almost got killed. Both times, luckily, a Bobby, otherwise known as a policeman, grabbed me by, "What are you doing, sir?" And he said, see the street down there? And they have it printed in major intersections for us dumb Americans. Look the other way. And finally, let me get my collar straight again. I figured out how to safely cross streets in England. How did I do that? I waited until I saw a little old man or woman, and when they crossed, I figured it must be safe. I could walk too. And it worked. Now, let me show you something. This is organic chemistry, and let's talk about chiral molecules. Here I have a molecule, and let's say there was an atom here, silver, black, yellow, red, different atoms. Then notice here, I have its mirror image. If I had a mirror right here, red goes to red, yellow to yellow, silver here, and far away black. So these are mirror images. But notice they're not superimposable. If I put this, the red and yellow don't match up, but the silver and black do. Now, if I rotate, didn't realize this is going to be a double show and tell day. But anyways, if I rotate this, now the red and yellow line up, but the black and silver don't. Here's black and silver, black and silver. So these two molecules are mirror images. Hold on. Yep, mirror images, but they're not superimposable, non-superimposable, and these are chiral molecules. And turns out, and I'll teach you later this chapter, your body has a way of distinguishing chiral molecules. And just like putting a key into a lock, if you've got the wrong key, guess what? The lock won't open. And if you have two molecules and your body needs this isomer, these are isomers, and they have another name I'll teach you later on. This might save your life. This might do nothing or kill you. And that's why some of the medicines are very expensive, because you need the right isomer to do the job. The other reason they're expensive is drug companies are greedy. Oops, hold on. My computer just said, I've got to play games on Dr. White. It went pretty long, too. All right, everybody see chiral center? Thank you. Now, when we talk about molecules, important thing is a chiral center. I'll never ask you what is a chiral center, but you should know that's an atom. And for this class, we're going to talk only about carbon. That's in a molecule that has 4 different groups, otherwise known as tetrahedrally bonded to it. If you notice, the molecule I just showed you is similar to this. The dotted line means it's going back away from you. The wedge is coming towards you. A and D are in the plane of a molecule. If we look at this here, yellow is coming towards you. That would be a wedge. Red is coming away from you. And notice these two are in the same plane like my hand. And that's a way of drawing 3 dimensions. Good news, I won't be doing anything like that in this class, but I just wanted to show you that. Now, we have what's known as a chiral center. And a chiral center has 4 different groups to it, bonded to it. Now let's just do one because we're running out of time. And the question is 3 points each, circle the chiral atoms, or I could have put carbons or carbon atoms. All right, now, quick thing. What is a chiral carbon? It has 4 different groups on it, either atoms or groups. Therefore, if something has 2 or more of the same atom on a carbon, it can't be chiral. So if we look at this, 3 hydrogens, that's out, 2 hydrogens, that's out, 2 hydrogens, that's out, 3 hydrogens, that's out, because it has to have 4 different things. If it has 3 or 2 of the same atom or group on a carbon, it can't be chiral. Now, let's look at this carbon. It has a methyl group, a hydrogen, bromine, and this whole long thing I'll call R. And notice this, this, and this are all different. Therefore, that's a chiral carbon. And I'd circle it, and I did. Now, let's look at this carbon right here. It has a hydrogen hydroxyl group, a methyl, and this whole thing here. And these are 1, 2, 3, 4 different things. Therefore, this gets circled. And those are the 2 chiral carbons. And that's what you should know how to do. Now, if I look at the time, we're almost out of time. Boy, time flies when you're having fun with chirality in your hands. Don't forget, my homework assignment to you is take your right hand and hold it up in the mirror and look what you see. You'll see this and prove to yourself your hands are not superimposable. If you really want to live dangerously, try it with your feet, only if you have a full-length mirror. But don't hurt yourself trying to pick your foot up to if you have this higher mirror. Don't. I don't want to get sued. But anyways, important announcement. Next Monday, I will be going through the lipids problem set, fats and oils problem set. Make sure between now and next Monday you do that. And don't forget, tonight at 6 to 7:15, I have my office hour. Please come by, say hello if you have any questions or need any help with anything or anything else I can help you out with. And don't forget, Wednesday is International Chem 170 turn on your webcam day. So make sure you're prepared to turn on your webcam so I can see your real people. Those of you who do, thank you. And with that, I just ran out of time. I'm going to let you out a whole 30 seconds early. Don't tell the dean. With that, I'm going to do my world famous goodbye. Gang gesund, be healthy. Goodbye. But anyways, good afternoon, everybody. Welcome to another exciting afternoon of chemistry, Chem 170, with your host, me, Dr. White. We got a lot to do, but first, a couple of public service announcements from me, the management, and I am. But anyways, first of all, don't forget tonight at 6 to 7:15 on Zoom, I will have my office hour. If you got any questions about anything, stop by and say hello and ask your question. Next, don't forget, coming up soon, if you want to do it, is the deadline for the extra credit project. Remember, the extra credit project is, yes, 10 extra points. And as I said when I first discussed it, it's on the sheet too. Send me your extra credit project before you upload it. Try and do it in advance, a couple more than just the day before. If there's any problems, I'll let you know so you can fix them. Or you can come to my office hours and discuss that with me, and I'll help you out. That way you can get 10 bonus points. All right, speaking about my hands, did anybody do the not extra credit, the homework project? Did you take your right hand and put it up the mirror and you saw, oh, look, my left hand. And if you want like this, it goes like that in the mirror. But, and remember my famous joke, you know what this is, don't you? A spider doing push-ups on a mirror. But anyways, did you think about things in your daily life? Like if you were putting on your shoes, did you think, are my shoes chiral or achiral? Remember, chiral, something with a non-superimposable mirror image. Achiral, something with a superimposable mirror image. Now, pro tip, if it has in the description left or right like my left shoe or right shoe, immediately you know it's chiral because it has handedness. Anybody try and do their superimposable your hands and find out, oh no, nothing lines up because your hands are chiral. All right, now, on Monday, I was finishing up with and starting to talk about chiral centers. And a chiral center is a molecule that has 4 different groups. I can actually expand this definition, or 4 different atoms, or a combination of 4 different groups or atoms. And turns out, and I'll explain more today or on Monday, why having a chiral, in our case, carbon, is quite important. But anyways, chirality, or chiral carbon, you have to have 4 different groups. When that happens, that's considered a chiral center. But since this is organic chemistry, I'll just be talking about chiral carbon atoms, which, being a lazy organic chemist, I shortened down to just carbon atoms. Oh, I forgot to mention, today is International Chem 170 Turn on your webcam day. So make Dr. White happy and turn on your webcam. For those who have, thank you. See, you're making me happy. So don't forget, it's International Turn on your Chem 170 webcam. Oh, people are doing it. I see real faces. Thank you, Anna. And everybody turn it on. All right, let's go back to chiral centers and chiral carbons. Everybody see my whiteboard? Thumbs up, people. Thank you. All right, now, we went through this last time, but I'll do it for you. Everybody see my screen? Oh, I see everybody doing their thumbs up. Thank you. And the question is, circle the chiral carbons. Now, it's time for Dr. White to give you a real good tip. In order to have a chiral carbon, it needs 4 different atoms, 4 different groups, or a combination of 4 different atoms or groups. Oh, wait, can I do this? I can make me bigger. Ha ha, look out. And you're bigger too. All right, now, let me get me smaller. But it has to have 4 different groups or 4 different atoms or a combination of 4 different atoms or groups. Therefore, if you have a carbon with 2 or more of the same group, it can't be chiral. Also, if a carbon is in a double or triple bond, it can't be chiral. Let me say that again. If you have 2 or more of the same atom or group on a carbon, it cannot be chiral. If you have a carbon in a double bond or triple bond with either another carbon or another atom, it can't be chiral. So let me do this one. And the question is, circle the chiral carbons. Oh, look, 3 hydrogens on that, and that's out. 2 hydrogens. Remember, if you have 2 or more, the same atom or group, you can't have 4 different things on a carbon. So this carbon's out, and here again, 3 carbon. I like my sound effects today. And this carbon has 3 hydrogens. That's 2 or more, and that's out. Ooh, that's an awful looking check. That's better. So that leaves us with these 2 carbons to consider. Now, let's look at this carbon right here as a hydrogen hydroxyl group, a methyl group, and this I'll call R, all those carbons in a chlorine. So I have hydrogen, hydroxyl, methyl, and R. That's 4. So this is a chiral carbon. Now, let me erase these circles because I was just using that. Now we have this carbon as a methyl group. It has this whole thing I'll call R. Let me get rid of this R. As a chlorine and a hydrogen. And therefore it has 4 different groups or atoms or combination: hydrogen, chlorine, methyl, and what I'll call R. So this would be chiral. And that's how you do it. All right. Oops. This is SH. Let me clean this up. This is a double bond. And why don't you circle all the chiral carbons in that molecule? Like I said, I'm going to share the fun today. Well, I always do. And for those of you who turned off your webcam, turn it back on, please. Somebody who's one of our students knows, oh no, I'm missing the dog with the marker. Oh, good news. Since y'all have your cameras on, I can see nobody's got smoke coming out of your ears from being overtaxed by my question. Oh, I see someone's got their answer ready. Unfortunately, unless I unpin everything, I can't see it that well either can everybody else, but thank you, Tom. The dean will be happy. Some of my students like to do that. I don't. Shh, don't tell her I said that. All right. Anybody need more time? Yell out. Okay, let's take a look at B. And the question is circle the chiral carbons, 3 points each. Now, the quick way is look for carbons that can't be chiral. If it has 2 or more of the same group, or if it's in a double or triple bond, it can't be chiral. This one has 3 hydrogens, it's out. Oh, look at these 2 carbons, they're in a double bond, they're out. CH2, 2 or more are the same, it's out. And this carbonyl carbon is double bond to oxygen, that's double bond, that's out. So we just have this, and this carbon to consider. And if we look at the first one, this one, we have a hydrogen, a thiol group, a methyl, and then all this, and it's all different. So that would be a chiral carbon. Come on, eraser. All right, why is my eraser not wanting to erase? That's weird. All right, hold on 1 second while I do something. Let's see if this will help. For those of you who don't know about CCleaner, hopefully, let's see if that helped. All right, I'm going to shut this down and bring it back up again. Or better yet, I'll just do different colors, then I'll shut it down. If we look at this carbon, sorry about that, technical difficulty, I don't know why. It's been good to me all semester. All right, this carbon has hydrogen, bromine, this whole group here, and this whole group here. It's different. 1, 2, 3, 4 different atoms or groups of atoms or molecule or groups of atoms, and therefore that's chiral. And finally, let's look at this carbon right here, and that shouldn't be a 2. Sorry about that. And you have a hydroxyl group, hydrogen, this carbonyl with the hydrogen, and this whole thing right here. And those are different. 1, 2, hydroxyl group, 3, hydrogen, 4. Therefore, that would be chiral. And that's how you do it. But before we go forward, let me close this. Let me open it again. And now it's working again. Don't ask me why it freezes up. I think one of the more complex structures I draw. But anyways, we're back on track. All right, let's do one more. Again, the question is circle all the chiral carbons. Does everybody see the ring on your screen? Think about it. 6 months ago, if I said, do you see the ring on your screen? Would you know what I was talking about? Think how much you've learned, and you should all be proud of that. Oh, I'll give you a hint. Remember, 4 bonds to carbon. Is today Friday the 13th? Wait, Friday the 13th has been lucky for me. Is today Wednesday the 24th? Oh no, that's why I'm having problems. Part of it is I've got so many things going on this computer with the tablet, Zoom, my webcam, and everything else. Sometimes it will freeze up like that. for one of the applications. I know if I just log off and log back on and use CCleaner, it always clears it up. All right, anybody need more time? Thumbs up, people. If you're done, give me thumbs up. All right, the thumbs have it. Thank you, thumbs up, people. All right, now let's take a look at the ring. And before I do, let's show the hydrogens. This carbon has 2, because there's 1, 2 bonds. There should be 4. 4 minus 2 is 2. This one has 2. This one has 1. This one has 1. And this one has 1. Now, as I taught you, the quick trick is if a carbon has 2 or more of the same group, it's out. 1, 2, that's out. And this one is out. 2 hydrogens, 3. But that leaves us 3 carbons to go, which this one, and this one. If you look at this one right here, it's got a hydrogen, chlorine, this part of the ring, and this part of the ring, which are different. So it has 4 different groups, and therefore, I'm going to circle it because that's chiral. And if you look at the next carbon next to it, this one, the same thing. It's got a hydrogen, hydroxyl group, and let me get rid of my little dots here. Oh no, I wiped out a hydrogen. Now, if we're looking at this carbon right here, it has a hydroxyl group, a hydrogen. These 2 carbons with a chlorine, and these 3 carbons right here, 2 carbons in a ring. And those are different. Therefore, this is chiral. And finally, this last carbon, same thing, methyl, hydrogen, and then these 2 carbons of the ring, and these 2 carbons with hydroxyl. So this would be, and therefore you have 3 carbon in the molecule with a chiral center. Oops, not what I wanted. Now my software would write glucose, which this is what the molecule is. I'm writing. And remember, this is by definition equivalent to, that's what the third, identical to this. So in glucose, one more time, everybody, circle the chiral carbons. Now, every intersection of the line here is really a carbon. So there's a carbon here, 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 and here. Oh, it makes my heart beat so nicely to see and feel good. See all of you working on where the chiral carbons. Thank you. It's called positive reinforcement. And it works. When you're done, give me a thumbs up. For those who don't have your webcam on, you can use your emoji. But remember, I think it was in this class that I changed the name of emojis. I'm going to call it Symboli. Uh-oh, it's Terrible Humor Wednesday. All right, I think everybody's done. Let's take a look at this. If I look at this carbon right here, notice it has 2 hydrogens, so it's out. This carbon here, which is really this carbon here, is involved in a double bond, so it's out. And what that leaves me with is this carbon right here, hydroxyl hydrogen, the aldehyde, and the rest of the carbons, it's chiral. This carbon right here, hydrogen hydroxyl group, these 2 carbons up here, the other carbons down here, 4 different groups, it's chiral, and then these 2 also. And glucose has 4 chiral carbons. And in order to have a chiral molecule, you need at least 1 chiral carbon. If you don't, it's not going to be chiral. Now, something I haven't really talked about, and the switch is off for this definition, but it's something I'll be discussing in a little while, so you'll need to know. There's something called stereoisomers. Those are isomers. Now, an isomer is different molecules that have the same molecular but different, can have different structural, but a stereoisomer are isomers that have the same molecular and the same structural formulas, but different in their orientation of atoms in space. That's why it's called stereo. 3 dimensions, stereo. Now, isomers whose, another way of saying that is isomers whose atoms are connected in the same way, but differ in their arrangements in space. And that's the stereoisomer, and that's the whole concept is called stereoisomerism. Aren't you glad I'm not doing enunciation quizzes? Oh, I could do that online. Turn on your mic and say this word. No, I knew a faculty member who did that in general chemistry, made his students name certain things and know how to pronounce them. Now, for stereoisomers, major feature is a chiral center. And that's because you have a rigid structure. Nitrogen, if you look at a quaternary ammonium salt, again, I'm never going to ask you what are the major features of stereoisomerism, but have you ever had an umbrella and you're in a rainstorm and it flips? So instead of going like this, it goes whoop. That's happened to me. I'm sure it's happened to you. Well, nitrogen in a quaternary ammonium salt can have 4 different groups, but it can go up and down, and therefore it's not rigid and it can't have, guess what? Stereoisomers. Now, if you remember, it's show and tell time. By the way, did anybody happen to wash your hands since we met? I hope you all did. That'd be pretty funky if you didn't, especially in our COVID-19 environment. Did you think about making micelles? Anyways, back to here. These are 2 different molecules. They're identical. This carbon has a black, a silver, a yellow, and a red. So does this, but they're not identical because they're not superimposable. And these are stereoisomers. And turns out a lot of molecules in your body and nature are stereoisomers or 1 isomer, and it makes a big difference. I'll talk more about that. Now, switch is on. Big time. Hold on. It's Subtle Wednesday. Aren't you glad I don't expect you to be able to read my mind? And that's enantiomers. Now, what is an enantiomer? A molecule with a non-superimposable mirror image. And we have what's called enantiomeric pairs. And if I were to ask you, draw the enantiomer of glucose, and let me switch to my whiteboard. I'll never ask you to memorize the molecule glucose, but I can give it to you on a test. Wrong thing. Right thing. Wrong color. Hopefully I spelled enantiomer right. I sometimes spell it wrong. Anyways, if there's a spelling error, you'll know why SP is spelling error. All right, so let's look at this. All right, if I give you this and I'd show you this structure and I ask 3 points each, draw the enantiomer for that, what am I really asking? I'm asking you to draw the mirror image. Well, how do you do that? Now, you don't have to do what I'm going to do, but I like for a mnemonic device for my memory and brain to put in my mirror like this. This is my mirror. Now, you don't have to do this, but it helps me. Now, if you take and hold this molecule up to the mirror, you're going to see a reflection. Now, an aldehyde, since it has an achiral carbon, it's not chiral. I can just draw it like this. I don't have to worry about a mirror image. Same thing right here, this carbon. Now, I'll give you a second or two to get it all written down, what I've done so far. And I'll get to look at everybody's faces. Hi, everybody. Oh, Dr. White's so happy. Thank you for turning on my, see how easily I'm pleased? That and talking about organic chemistry, I'm in a good mood. All right. If you take your hand, and let's assume there's a mirror right in between, and you hold it up to the mirror, you'll see your left hand. Now, when you look, here's the mirror in between. Here's the, what I'm looking, here's my hand, here's the image. What do I see first in the image of them in the mirror? What's closest to the mirror? The palm of my hand, I'll see. And that's true with anything. When you hold it up to a mirror like this, I'm going to see the yellow and red in front and the silver and black behind. And that's because what you see in a mirror first, put in a mirror closest, that's what you'll see to reflect. Ooh, do you see my reflection? My right hand? Never mind about the spider. I love that joke. So what does that mean? If we look at, and thumbs up people, do you see my whiteboard on there? If you look at this carbon right here, what's closest to the mirror? Hydroxyl group. That's what you'll see. What's farthest away? Hydrogen. What's closest here? Hydroxyl group. What's farthest away? Hydrogen. What's closest here? By the way, the closer I get to me, the worse my hydrogens look. Do you believe that? Nah. Just not doing it well today. What's close to the mirror? Hydrogen. What's farthest away on this carbon? Hydroxyl group. And the last one, what's close to the mirror? Here's my mirror. Hydroxyl group. What's farthest away? Hydrogen. And this is the answer. That's the enantiomer of glucose. It's a non-superimposable mirror image. Now, this is called a Fisher projection. And I'll teach you later today or Monday why, when you're doing, is this superimposable or not, Fisher projections, you can only pick up and lay on top of another Fisher projection. You can't rotate it to see if it's superimposable. Let me say that again. Fisher projections and their mirror images, you can just pick one up and lay it over the other. You can't rotate it to see if it's superimposable. And therefore, this is superimposable on there, and therefore it truly is the enantiomer.
So, quick question.
You're
So if we,
didn't do it quick enough.
okay.
Go ahead.
So would this actually be OHC for the second one instead of if it's the mirror, or does that?
Which one are you talking about?
The very top, the CHO.
Well, you could write the mirror like this.
Yeah, that's.
But since it's a achiral carbon, it's going to be superimposable on its mirror image. It doesn't. This. One of the things I haven't mentioned. Ooh, this is a good time.
So I mean, I'm just saying the reason I'm asking.
There's a reason why you're asking a question, which I neglect to talk about. Have you ever gotten some of those things where you assume everybody knows what you're talking about because everybody in your world knows that? Well, you don't. All right, let's assume I have bond between two carbons right here. This black and this black is a carbon. This is a carbon-carbon single bond. There's free rotation around it.
Yeah.
So the one here can rotate around, and because it's achiral, it doesn't matter which way you draw it. Now, if you want to draw it as a mirror image, go right ahead, because I'll mark it okay. But I'm a lazy organic chemist, and if we don't, we don't. Organic
I just didn't know if there would be a hydrogen bond going up to the oxygen.
Well, it's on there, but we're only looking at carbons.
Okay.
All right.
Sorry.
There's nothing to be sorry about. Remember, in my class, there's no such thing as a dumb question ever. Okay? Ooh, Dr. Wake got serious there. Look out. But I am serious about that. All right. It's time for you to have some fun. I don't know if this is a real molecule or not, but it's something for you to have fun with. And the question is, draw the enantiomer. Three points each. Have fun. Oh my goodness, I get to see all my friendly students out there in Zoom land. What do you call out there in the Zoom meeting? Zoomlandier? Get to see most of you have a neater place than my office. It's a never-ending battle to keep it clean. In fact, this weekend I'll go to war with my office again, do a cleaning, and within a month it will be a mess again. Not a mess, but. And when you're done, give me a thumbs up. All right, I think everybody's got their thumbs up almost. Everybody does. Let's do it. So what does it mean? Draw the enantiomer. Means draw the mirror image. And it'll be non-superposable. I'll never give you something where there's no enantiomer. I'll say that in a second. So first of all, I'm going to do my backbone. 1, 2, 3. The bottom here, I have CH2OH. It's a chiral. Here I have my aldehyde. Set up extra line fell in there. And now here's my mirror. What's closest to the mirror in the first carbon, you'll see first. What's farthest away, you'll see farthest away. Next carbon, what's close to the mirror, hydrogen. What's farthest away, this one. And finally, the last one, what's closest to the mirror, this one. And what's farthest away, this one. And that's how you draw an enantiomer. If you want this weekend, if you happen to be on Zoom with friends or you know people are fully vaccinated that you can be with, you can impress them and show them how to draw enantiomers. People don't like to hear that. But that's an enantiomer. Now, switches off for this. There's another type of stereoisomer, which you learned about, but I didn't want to confuse you with the name at the time, and that's called a diastereomer. And those are stereoisomers whose molecules are not mirror images of each other. An example of that would be sister trans 2-butene I showed you long ago. They're non-superimposable. They're stereoisomers because they differ in how they're connected in space, but I'll never ask this on a test. But if you ever happen to run into anybody talking about diastereomers, you'll know what I'm talking about if you remember this. All right, let's talk about Fisher projections. Before that, I have a sad story to talk about. You've heard me talk about Emil Fischer, great German organic chemist, a great one. Unfortunately, Emil Fischer died way too young. Emil Fischer is the one who figured out how to make esters. It's called Fischer esterification because he discovered that or created it, which is, that alone is a great achievement in organic chemistry. But what he's well known for is his work with sugars. And it killed him. How did it kill him? Well, back in the late 1800s, early 1900s, especially if you're working with sugars, you'd make derivatives. And there were certain derivatives that you would make, which would be solids, and you could get good melting points out of. If we were in the lab, I'd talk more about it. But anyways, they had a bad habit back then. They taste things. You don't do that in the lab. Well, they did. And one of the most important derivatives is reacting 2,4-dinitrophenylhydrazine with a sugar, smaller ones, and you get a nice solid that you can get a very good melting point, and that helps you elucidate, that's a fancy word for figure out the structures. And all the smaller sugars, Emil Fischer figured out. But he died of 2,4-dinitrophenylhydrazine poisoning because not all that would react. He tasted it, and eventually it killed him. Sad but true. But what Emil Fischer figured out, which is also named in his honor, is Fischer projections. Here's a molecule, 3 dimensions. How do I write it in 2 dimensions on a piece of paper, but still showing the 3 dimensions? Switches off for this, but is in other classes you might need to know this. So what you do is, here's my 3 dimensions. Again, switch is totally off for this slide, but the black wedge means C is coming towards you. The dashed wedge is going away from you behind the plane of the paper. In the plane of the paper are A and D. And if you rotate this, 90 degrees, then flatten it out. You'll find C is on this side, E is here, D is on the bottom, A is up. And what this really means is A and E are coming towards you, and C and E are coming towards you, and A and D are going away. This will not be on a test. But one time I did, and everybody always got it wrong. And I figured, nah, I got better things to talk about than spending a lot of time teaching students how to do this, because you're not going to do this. Now, what I mean by this is, here is the Fisher projection. Yellow's coming towards you. Red is, let's do it this way. Red is coming towards you. Yellow is behind or farther away. And in this plane right here are black and silver. And if I rotate it like this, I'm not going to do it, but smash it flat. Red will be on this side, yellow here, black, silver. And you see it like that. But in reality, it's coming towards you like these. These two are going away. And each carbon in a Fisher projection shows that, even though it's only 2 dimensions. And it was a great, I guess you call it, invention of his that made him even a greater chemist, the work he did. Well, like I said, unfortunately, organic chemistry also killed him. Quick story. For a while, I thought I did myself in. When I was a postdoctoral fellow, I was working with, and I made it myself, high purity ozone. Ozone is extremely dangerous. And I came down where I had this fever, I felt weak, and I didn't know what the heck was. And a couple months earlier at the chemistry department, a student actually destroyed his liver, almost killed himself, part of his liver, by working with chemicals and getting exposed to them. And as careful as I did, I could still smell I was getting some light exposure to ozone. So I went to my doctor, and this went on for a couple of weeks, and I was getting concerned. And this doctor, who was very good but had a bad sense of humor, called me up one day and said, I figured out what's wrong with you. And he said, I need to talk to, actually, the way it went, he got in touch with his office. He needs to talk to me. So I called him and said, I've got good news and bad news for you. And I said, all right, what's the good news? He said, I know what you have. And he said, all right, what's the bad news? There's no cure for it. And guess what? I came down with mono, which unfortunately got worse when I had hepatitis. Luckily in my building, there was a nurse who lived there when I lived in Chicago. And every night for about 6-7 weeks, when she'd come home from her shift, she'd knock on my door and say, open your eyes. And she'd look to see if I'd gone jaundice, yellow, which means you're in serious problem. But anyways, that's what killed Emil Fisher. And this is a Fisher projection. And that's what this means. C and E, like yellow and red, are coming towards you. A and D, like silver and black, are going back behind the paper. And if I look at the clock, I'm going to do something I haven't done all semester, because for some reason, we're a little behind on schedule. Right now, we're on schedule. And on a Wednesday, what I normally do, and if we were face-to-face, is say, all right, let's take a 10-minute break, but today we'll just take a 5-minute break because we're on Zoom, and then we'll do the lab, and today's a quick lab, and I can get you out early. Thank you, Dr. White. You're welcome. So everybody, let's take a 5-minute break. Let's see, it's 10:48. Why don't you come back at 10:48? Wow, did I read it wrong? 1:48. Why don't you come back at 1:55? We'll take a couple minutes. Let's get going. Good afternoon, everybody. Welcome to another sunny afternoon of Chem 170, Organic Chemistry, with your host, me, Dr. White. Some important announcements. First of all, a week from this Wednesday will be test 4 test 4. And I'll talk more about it on Wednesday. By Wednesday, I'll put out an email, an announcement with the point breakdown and everything. But test 4 will cover fats and oils, the lipid chapter, and carbohydrates. And that will be that. Also, if you looked at it, next Wednesday, a week from this Wednesday, the 5th, is the deadline for the extra credit project. Remember, the extra credit project is optional, but if you do it, it's 10. Yes, 10. 10 points. Now, as I mentioned when I talked about it, and you can find it on D2L, if you email me or if you stop by my office hours, which I'll have it tonight and Wednesday night, starting at 6, I will check it over. And if anything's wrong, I'll help you correct it, which means if you take the time to do it, you can get, yes, 10. Yes, I still have 5 fingers on each hand, 10 points. Uh-oh, it's starting to be a pretty awful humor Monday. But anyways, don't forget that. Also, if you haven't, I think most of you have, but a couple haven't, make sure you turn in your labs on time. As of yesterday, I'm pretty much caught up with everybody's labs that you've turned in, checking D2L to make sure if you handed in a lab, I have graded it. Well, in that case, let's get going. Did anybody happen to look around your house or different things and think, is it chiral or achiral object? Like your hands are chiral. Anything that has left and right in this thing is probably chiral. Remember, chiral, non-superimposable mirror image. Achiral, superimposable mirror image. Your hands are mirror images, they're not superimposable, and therefore they are chiral. Let's see, what do I have around here real quick? I don't have anything real quick. Trying to find some, this would be superimposable with its mirror image. And it's superimposable. So Post-its with nothing written on them are superimposable. Therefore, they're achiral. Oh, I could put that on a test. I gave it away already. All right, let's get back to work or fun. Now, if you remember, I was talking about enantiomers. Enantiomers are non-superimposable mirror images of molecules. And if a molecule has a non-superimposable image, it has an enantiomer. As we did last time, draw the enantiomers of a couple of sugars I had. And here's glucose. And let's start out with a little fun. Oh, I haven't done it, and I figure Wednesday would be a good day. I think it's better Wednesday. Wednesday, I'll go through the lipids problem set, fats and oils. Thumbs up, people. You see my whiteboard? Thank you. And here's one for you to start out this nice, beautiful day. Tomorrow is supposed to be nice and warm. I wonder if I'll have to turn on my air conditioner or not. I've got it uncovered. But anyways, draw the enantiomer of that compound. 3 points each. And for those of you who came in late, don't forget, it's still, I've expanded it to a month, not a day. It's National Turn on Your Webcam Month for Dr. White. Please. That way I can see your real pictures, people. I can see your pictures on my screen, so you're alive. They're alive. Yay. Good news, I don't think I killed anybody this semester or last or the others by talking about organic chemistry or any other way either. I hope you all had a nice time since we last met. All right, thumbs up, people. Everybody done? I think everybody's done, so I better get to work. Now, what is the enantiomer of a compound? It's its mirror image. Now, I like to draw in the mirror because it's a mnemonic device, memory, or it helps me. You don't have to, but achiral carbons, you don't have to draw the mirror image. But if you wanted to draw this one here, like this, that's fine. Same thing down here. If you wanted to draw this, that's fine, but you don't have to. But these are chiral carbons. Remember, chiral carbon, four different groups, 4 different atoms, or a combination of 4 different groups and atoms. Same thing here. So if we look at this hydrogen, it's closest to the mirror. It's what we'll see first. The hydroxyl group is farthest away. This hydroxyl group is close to the mirror. I'm a little off base here, and I think I drew it wrong. Hold on. So used to doing glucose. Oh, Dr. White messed up. All right, hydrogen closest, hydroxyl group farthest away. Next carbon, hydroxyl group closest to the mirror, what's farthest away, hydrogen, that's what you'll see. And finally, bromine, closest, farthest away, hydrogen, and that's how you do an enantiomer. And I mentioned diastereomers, which I'll never ask on a test, are stereoisomers whose molecules are not mirror images of each other. Cis and trans are an example of that. Now, I talked about Fisher projections, which I will not put on a test. Here's 3-dimension, draw Fisher. I should ask my thumbs up, people. Can you see that on the screen? Thank you. Now, one thing I should ask, which I think we might have done, you don't have to learn the structure, but this is glucose, and we'll talk more about it today. And I would ask you, circle the chiral carbons. Remember, each intersection of a line is a carbon here, here, and here. So why don't you circle the chiral carbons? And all of you have your camera on. Thank you. Oh, it warms my heart. Things that warm my heart are good things. Remember, chiral carbon has 4 different groups, 4 different atoms, or a combination of each. If you're done, give me a thumbs up. I think everybody just gave me the thumbs up, so I better get to work. All right, if we look at this carbon, it has hydroxyl, hydrogen, this aldehyde, and the rest of the chain. That's 4 different groups. Same thing with this carbon, hydroxyl, hydrogen, these 2 carbons, and these 3. That'd be 4. And if we look at this one, same thing, 4 different groups, and this one, 4 different groups. So in glucose, there are 4 chiral carbons. Now, one of the things I won't put on a test, but I think it's interesting to know about is stereoisomers, both enantiomers and other things, diastereomers. Let me go to the whiteboard, I got more room. And hopefully everybody, did you see my whiteboard? This won't be on the test, but I thought it'd be interesting. If N equals the number of chiral carbons in a molecule, then the number of stereoisomers is 2 to the N. Now, glucose has 4 chiral carbons, 2 to the 4th power is 16. That means glucose type molecules, there's a possible total of 16 stereoisomers. One of them is its enantiomer, and then the other 14, the original enantiomer, other 14. Mother Nature only picked glucose as what she uses, where she had 16 possible isomers, she only picked 1. And that's how good of an organic chemist Mother Nature is. I mean that sincerely. Now, because when you have a chiral carbon or more, the molecule is chiral, meaning it can exist in right or left form. And in order to detect that or talk about certain monosaccharides, mono 1 saccharide, carbon, sugar with either aldehyde or ketone, and the switch is off for here, but you may need this for other classes. There's the DL designation. And this works based on the left or right of the highest numbered chiral carbon with the hydroxyl group. In an aldehyde, which really this is 1, 2, 3, 4, 5, 6. This is not chiral. So this is the highest numbered. If the hydroxyl group is on the right, we put a D in front of the name. D-glucose. If it were on the left, it would be L-glucose. And let me do one more thing, and then I'll come back to this. And again, switch is totally off. This will not be on test. Now, when we talk about enantiomers, they're non-superimposable mirror images. And turns out they have all the same physical properties except two things. And one of them is how it's called optical activity. And the other one, again, switches off now, the reactivity, how it reacts with other chiral compounds, which turns out to be very important. Now, what is optical activity? And how many of you are familiar with plain polarized light? Light, like hitting me right now, ouch, that was an awful joke. I'll never use that again. But anyways, light that's hitting you comes in as waves. Light can be a particle and a wave. It can be both at the same time. I'm not a physicist, so I'm not going to explain why. But think of it as waves. And the light, white light, coming in at this way, it can come in at this way, actually comes at you, the waves 360 degrees. Well, it turns out scientists, chemists, have found that if you use a filter, you can just have one wave come. Does that look like it's coming right at you? One wave, not all 360 degrees. How many of you have ever seen or heard about plain polarized sunglasses or polarizing sunglasses? And they're pretty strong, work quite well. How? Because they're essentially, they filter out all the polarized, all the light except one wave, one degree. And that means most of the light is filtered out. And that one wave we call plain polarized light, you're putting it through a filter because it polarizes it. Now, when we talk about optical activity, a chiral molecule is an optically active compound. And what does that mean? It rotates plain polarized light to either the right or left so many degrees if you have one wave. So if you have a sample of stuff here and you put in plain polarized light, it will rotate it. If you had a detector where it was coming in on the detector at 0 degrees, it might rotate that light to the right or left, say 10, 15 degrees or more. And this is an important way of telling, do you have an optically active compound or is it impure? If you know it's pure, it should go so many degrees right or left, and it doesn't at a certain temperature, guess what? You don't have a pure substance. Now, when we talk about optically active compounds, again, switches off, but this might be useful for your other classes. You can rotate, if it's coming in at 0 degrees like this, you can rotate it to my right or my left. And there's no way of knowing what it will do until you go into the lab and measure it. You just can't say, look at a molecule and say, which way will it rotate plain polarized light? And when it rotates to the right, it's called dextrorotary compound. And dextro, I believe, comes from Latin for right. And you use a plus sign to designate that. When it rotates it to the left, it's levo or levorotary. I don't know, I'm not a sugar chemist. And you use a minus sign to show that. Now, quick Dr. White story. A couple of years ago, I had this one woman who was coming back to get her master's degree in nursing and needed to take organic again because it had been so many years since she took it. At this point, She said, oh, that explains the letters and symbols on the feeding bottles for intravenous feeding. And if you've ever been in a hospital where they feed you intravenously, I did when I had a major operation. I think I told you about my double hernia. Yeah, I did. We talked about inhalation anesthetics, ethers. But anyways, on the bottle, it has glucose because that's usually what they inject intravenously or feed people with. And on the label, it has something. Let's go out into the real world. I was just getting something. All right, I think I might have mentioned it before. Does everybody see the right here, the plus D glucose on your screen? And this is from Sigma Aldrich, which is not for medical use, but Sigma Aldrich is probably the finest company in the world for getting smaller samples of most organic chemicals, and others too, but mainly organic. They're located in Milwaukee. I think I first started ordering from them in the mid 1970s. Oh, I shouldn't have said that. But anyways, they are great. And notice you see D plus glucose. D tells you the hydroxyl group on carbon 5 is on the right. The plus sign tells you it rotates plain polarized light to the right. Let's see something. They give you information and more things you can learn about it. Oh, that one was discontinued. But anyways, I just wanted to show you that that's an important thing. All right, let's go back and talk about chapter 16 again. And here, I'm going to turn the switch off briefly, but these are things you may need in your other classes, so that's why I'm covering it. Notice we have an aldehyde here. As I mentioned beginning of this chapter, that you can write an aldehyde like this, or, which my software does for sugars, like that, same thing. And here we have an aldehyde. Now, when you have a monosaccharide that's an aldehyde, they call it an aldose. Again, switches off, and this is called a hexoaldose because there's 6 carbons, hexane, like hex. And this is glucose, by the way. Again, I'll never ask you on a test what's the structure of glucose. Next, if you have a ketone in a monosaccharide, it's called a ketose. Why they need that, I don't know. And here's my ketone. Here's R prime. And we could say this whole thing is R, or the other way around. So this is a ketone, and we call it ketose. How many of you ever heard of ketosis? And that's a problem with diabetics, where they have too much sugar, I believe, don't quote me on this, or it turns into ketones, and don't really quote me on this, but this is how it got its name, from ketosis. Ketosis. Interesting story. About, I think it was 3 summers ago, I had 2 students, and First day in lab, where I'm walking around talking to them everything, I see each one has this big thing on their arm right around here. And being the nosy person I am, and Dr. White can be very nosy, I walked up to one of them and asked, do you mind asking you, what's that? And he says, no, that's my glucose monitor that feeds to my cell phone by Bluetooth. And therefore, I don't have to take a blood sample to measure my sugar level. I said, oh, that's neat. Be careful when you're in the lab. Try not to get any chemicals on there or any time on you, period. And I had two students, and they both had were diabetics. One of the things I did, I asked them in private, and I've been doing this for many years, when I find out a student has a certain medical problem, or I don't know, problem situation, I ask them, if there's emergency, first of all, how do you want me to handle it? And second of all, do you have in your purse, backpack, or something, a phone number for emergency? And I've had people who are epileptic, and they told me if I go into a seizure, they explained what they want me to do. And one of them, because they didn't have insurance, unfortunately, she didn't want the paramedics called because she couldn't afford to go to a hospital. Well, luckily, none of them ever had a seizure, but I think that was my responsibility to be someone who could help them in an emergency, which I was prepared to do. And by the way, I've talked about this as sugar, and this is something you should know. A sugar is a general designation for a mono and disaccharide. So if you're at a dinner with someone, they say, please pass the sugar, guess what? They're talking about either a mono and disaccharide. Now, there's a special sugar you should know. First of all, I'll wait until you copy that down. Everybody got it? Okay. I don't have it on here, but you should know that table, I think I mentioned this earlier. This is not an IUPAC name, it's a common name that everybody uses. Table sugar is called sucrose, and I'll talk more about today what's the structure of sucrose. And so table sugar is a sugar because it's a disaccharide, which I mentioned earlier. I'll never ask you is sugar a disaccharide, but you should know that. And it's called sucrose. Now, forget about this right now. I'm going to come back to this in a little while. Switch is sort of semi-off here. I thought I'd just fill you in a little background. This is D-glucose. D, because the hydroxyl group right here on this highest number, chiral carbon, is on the right. I'll never ask that on a test. Turns out D-glucose is the most abundant sugar in nature. It's the sugar in your blood. And this molecule helps bring, I guess, nourishment. Now, Dr. White's well beyond his knowledge of the human body, because last time I took biology was freshman year high school. But anyways, this is the sugar in your blood. It's an allohexose aldehyde with 6 carbons, and it rotates plain polarized light to the right. This I will never ask on a test, but I thought you'd like to know that. Now, another sugar I just like to talk about, I won't have this on the test, is D-fructose. How many of you have heard of high fructose corn syrup? All you got to do is look at a bottle of ketchup or a lot of other things. And this is a ketohexose, ketone, 6 carbons. This turns out to be the sweetest sugar in nature. It's much sweeter than sucrose. Now, it turns out, and I'm not going to ever ask this, it rotates plain polarized light to the left. It's D-sucrose, because this hydroxy group is on the right, the highest, and I won't ask that. but it's found in corn syrup, or you can modify corn syrup so it has a high level of D-fructose. And for those who are not familiar with the food industry, I don't know how many years ago, 10, 15 years ago, I might be off by a couple of years, uh, organic chemists, not me, but found a way to modify corn syrup so it was extremely high percentage of D-fructose. That meant it was super sweet, and corn syrup is super cheap, a lot cheaper than table sugar sucrose. And most of the food industry, where they would use sucrose right here, switch to cheaper D-fructose. Now, I won't talk about it now, but maybe later today I will, or next Wednesday, this Wednesday. A lot of the mothers groups and other concerned citizens have come out and said, oh, D-fructose is causing a lot of the problems in our children, and it's dangerous. And they had a whole list of diseases and Dr. White doesn't believe that. I'll explain why, yes, having this high is not a good thing, but it's not just the D-fructose. Now, just like here, D-glucose can form a cyclic form, and I'll get to that. And D-fructose can form a cyclic form here. Now, these cyclic forms that I'm showing you are called Hawthorne projections. And the first time I tried teaching organic at ECC, I tried teaching students what this means. This is a three-dimensional molecule where you show two dimensions, show it on paper this way. And students had the worst problems. I realized it wasn't worth the effort to spend time on something nobody could master. I even have a little difficulty. So I just wanted to mention it's called Hawthorne projection. It's a two-dimensional structure notation that specifies three-dimensional structures of a cyclic form of a monosaccharide. Good news, it won't be on the test and won't ever be on a final. All right, now let's talk about the cyclic form, because this is very important. But it's time to show how Dr. White came up with a better way of teaching you, the students, that. And first, remember I promised a long time ago, no new reactions? Wasn't that long ago, at the end of test number 3 material. So let's look at something from test number 2. And test number 2, you take an aldehyde or ketone when R prime is H, it's an aldehyde. When it's carbon, it's a ketone. React it with an alcohol and acid. What happens? Keep your eye on the carbonyl carbon, that attacks that. And what you get, what's attached to that carbonyl carbon, R prime or H and R double prime, this becomes an alcohol and oxygen. And this is from test number 2. No new stuff. I'm going to draw the aldehyde here like an aldehyde that an organic chemist, not a sugar chemist, now it turns out one thing I haven't talked about is reaction rates. We talked about adding catalysts to make it go quicker. If you notice up here, I'm adding an acid catalyst. But it turns out, let me finish writing this molecule because it's half done. That's not polite. Now it's done. That when you have a reaction involving starting materials that are in the same molecule called intramolecular reaction, it goes a lot quicker. And usually you don't need always a catalyst. When you have separate molecules intermolecular, then a lot of times you will need a catalyst to make it go quicker. How many of you have ever taken an international flight? Dr. White has gone to Europe a lot on business, and that's when you go between two countries. And intra would be if I took a flight inside the United States, even though they don't call it. Now, let's look at something specific. This carbon right here, it has a hydrox group on a carbon. It's an alcohol. Here's my carbonyl carbon. And this will come on and attack that just like up here. Now, instead of having students draw the Hawthorne structure for the reaction product like I had in the slide, I came up with a better idea. All right, first of all, what's not involved in the reaction will not change. You've learned that. So I'm just going to redraw it. Now, the carbonyl still has the hydrogen, just like here. It's still bonded to this part, which would be here. But now this oxygen, which is this oxygen right here, will bond all the way to here. This is an actual bond. Here, this is an arrow showing where the electrons, and this will open it up to this hemiacetal. And this carbon here is this carbon here. So this reacts to form the cyclic form of glucose. Now, couple things. First of all, if I put on a test this, you should know how to get to this product. If I put the product on the test, you should know how to get to the starting material. Why is this important? Because if this didn't happen, we wouldn't have any carbohydrates, which you know as starches, on our planet. We wouldn't have also any trees or grass or anything growing. Is that important? You better believe it. Oh, I was just going to do a generation gap thing. I will. You bet your sweet Bippy. Nobody knows what TV show that came from. It's called Laughing. Go to YouTube someday. Anyways, you should know. Let's go through this. Aldehyde or ketone, alcohol, acid catalyst. And by the way, that's bonded to there. Hemiacetal or ketal. Now, when it's intramolecular, we do not need the acid catalyst, and it's in equilibrium. Here's the hydroxyl group right here. And this attacks that carbonyl carbon, which I show you right here. And it opens it up to what you see right there. And you should know how to do this. And by not having you learn the, by the way, this longest world's ugliest carbon oxygen single bond is this one right here. And this goes from this atom bonded to this atom. Here I'm just showing electrons, so you don't put an arrow on this side. You're actually showing a bond. Is everybody clear on that? And why don't you try it? What would be the product of that reaction? And I'll help you out today. All right, if you're done, give me a thumbs up. All right, looks like I saw a lot of thumbs, so I better get to work. Now, here's my carbonyl right here, and it's always the hydroxyl group on C5. 1, 2, 3, 4, C5. And that hydroxyl group, alcohol really, will attack here to form this bond and open up the carbonyl carbon to a hemi-acetal. Whatever is not involved in the reaction, I'm just going to rewrite because it's not going to change. However, this oxygen right here will react to the carbonyl carbon to form a carbon-oxygen bond, this one right here. So instead of asking you to learn Hawthorne projections, here's the world's ugliest, longest carbon-oxygen bond. That's this right here. Here's my carbonyl, which becomes this carbon, and will also have an alcohol on it. And that's how you make the cyclic form of glucose, because this molecule here, which I'll never ask you on a test to draw glucose, but this is glucose. Now, instead of rushing, I'm going to do something a little different. Let's take our 5-minute break now, come back at 1:50, and we'll continue. Dr. Wood's going to get up and stretch. I'll see you in 5. Oh no, I'm late. Time to start again. All right, everybody back. Apologizing for being a minute late. Mail came and so did something from Amazon. Sort of like getting a gift. Not really, I bought it myself, but it's always nice to get stuff you buy for yourself. But anyways, which is easier? To see this and have to write this, or do it this way? I hope you all agree, at least I've found from experience for students, this is the easier way. And don't tell anybody I'm being nice. Shh. But anyways, that's for glucose. Now, if we go back and we look at fructose, now fructose is a ketose, but it's a ketone. And hold on a second while I write this down, because I always remember glucose. I get one of the hydroxyl groups on fructose wrong. So I'm cheating now, not really. All right, let's get to work. Now this can form a cyclic form also, which looks like this, which is also a Hawthorne structure, which students get confused by. So once again, Dr. White to the rescue. Let's take a look at this one. Now remember, there's a carbon there. And this is fructose. And it's in equilibrium with its cyclic form. And again, let me remind you, you have a ketone or aldehyde plus an alcohol. If you have separate molecules, you need an acid catalyst, and this attacks my carbonyl. What's attached to my carbonyl? Our prime can be hydrogen or carbons, and it's either a ketone or aldehyde. And this opens up to this, just like we saw before. However, now, where's our alcohol? Turns out in fructose, it's the same alcohol, the hydroxyl group on carbon 5. And here's my carbonyl, this right here. And now this attacks that carbon, just like this attacks the carbonyl carbon. And what's unaffected, not involved in the reaction, I'll rewrite. Okay, and this oxygen right here will be bonded to the carbon. This one right here, that's this one right here, and this long bond here is this bond right here. And what else will you have on that carbon? A hydroxyl group. test, if I were to give you this, you should be able to write the structure for the product. If I give you the product, you should be able to write the starting material. And if this didn't happen, we wouldn't have any table sugar. Oh no, that wouldn't be good. So is this important? Well, in my book, having both high starches and table sugar, disaccharide, is pretty important. And you should know how to do this. So I'm going to let you try it on your own. And let me write down here in case you forgot. If it was intermolecular, you need an acid catalyst. And there you go. Oh, did I tell you the closer it gets to June, the uglier my hydrogens get? That's better. And when you're done, give me a thumbs up. I think everybody's done because I saw a lot of thumbs. So I better get to work. Now, in either glucose or fructose, it's always C5. This would be 1, 2, 3, 4, 5. Carbon number 5, organic chemist shorthand is C5 carbon 5. And this is this alcohol, which attacks the carbonyl carbon to open it up and form this bond. So this will attack my carbonyl carbon right here. And that's the only thing involved in the reaction. And it'll open up to this carbon. So what's not involved in the reaction, I'll rewrite. That's not hard. This carbon is this carbon right here, which is this carbon. And Dr. White made a mistake, which I can erase immediately and fix. And this oxygen here is this oxygen, which is bonded to my was the carbonyl carbon. And notice it has a hydroxyl group on there. And this is a cyclic form of fructose. And you should know how to do that. Now, next, let's talk about reductions. I haven't used terminology of reactions. Reductions is also one type of reduction, is hydrogenation. And says, see board, well, I better get to work. I'm not the board, so let's get the board on there. Long ago, test number 2 material. If you take an aldehyde or ketone, and I better ask, everybody see my whiteboard now? Thank you. And you have a pi bond, which you break. What's attached to carbons? You don't break carbon single bonds, but you break the pi bond, and each atom of the double bond gets a hydrogen. This is called hydrogenation. It's also called the reduction, or you reduce the aldehyde or ketone. It's interesting. I always remember glucose, but fructose. Now, this will not react with an alcohol. And I'm going to let you have some fun right off the start. What would be the product or products of the following reaction? Ooh, I just learned how to make your pictures bigger on the screen, which I'll undo now. Somebody give me a yes or no with your head. Have I talked about Barkeeper's Friend in this class yet? Did I talk about hair and grease removal product in this class yet? All right, we got time today. Bad, Dr. White. All right, let's do this. I think everybody's done. What do we have here? Well, we have an aldehyde, hydrogen, and a catalyst. Here's the general reaction. You're not going to break carbon-carbon single bonds. And what's not involved in the reaction, I can just rewrite. Now the carbonyl carbon, which is this carbon, you break the pi bond, and each atom gets a hydrogen. And I can rewrite this if I wanted to. You don't have to, but there's a reason why I'm doing it. And this is another way of writing it. Now, this molecule has a common name, sorbitol, OL. It's all alcohols. There are actually 6 of them. And let's go out to the real world right now. Everybody see sorbitol on your screen? All right, I'll mention it again that Wikipedia is so heavily policed in chemistry, especially organic chemistry, that whatever you find is generally correct. Now, sorbitol has this structure they show right here. Every bend in a line is a carbon. 1, 2, 3, 4, 5, 6. This shows stereochemistry like the Fischer. And this is what you just made. Now, what is it used for? Good question. And sorbitol is a sweetener, and it's made by the reduction of glucose, taking glucose and reacting with hydrogen in a catalyst. And it's a sweetener. And one of the places you find it in is diet foods, because it's hard for your body to break this down. Therefore, it's low calorie. And the other place you'll probably find it, let me do this. If you go to your local big box store or drugstore, and you know how most of them, like all of them, sell over-the-counter stuff, medicine, like cough syrup and other things. If you look at the cough syrup, if you look on the label halfway or near the end, you'll see sorbitol. Now, there are 2 reasons they put that in there. One, it adds some sweetness without adding calories, which, oh, I'll take that stuff, it's sweet. And they do that in a lot of medicines over the counter. The other thing is it's very thick or viscous, like honey. Therefore, when they put it in with other liquids, what you're buying is thicker. And you've been conditioned, ooh, it's thicker, that must make it better. No, but you've been conditioned that, and they do things like that. That's a secret, don't tell anybody. I'll see you on Wednesday. Don't forget, I'll go through the fats and oils problem set. Don't forget to hand in your lab. And with that, gehen gesund. I'll see you on Wednesday, unless you stop by for my office hour tonight. Bye.